Hello students, in this video we'll discuss complex valued functions which have primitives in a certain region and see how to evaluate certain complex line integrals. So let's recall, if C is parameterized by z of t, a complex valued curve for t between a and b. Of course, here, we know that z is a complex curve, so typically curves would be like an x of t, y of t. But now I'm writing them as u of t, the real part, plus I of t, iv of t, the imaginary part. So they're complex valued curves. Then we have what? Then we have the integral over c of f of z dt, dz, is by definition, and this is well defined by previous work, a to b, f of z of t, z prime of t. I'm assuming the curve is smoothly parameterized. dt. Okay, good. Now, let's look at several examples of this. And so a classic example that we're going to need over and over and over again. And so here's a classic example. So classic example. It's classical and useful. Let's find integral, and I'm just going to say over the t, which represents the unit circle over here. Integral over the unit circle, that's a curve, right? Of z to the power n dz for any n in z. Okay, so let's figure this out. This is this is the very, very beginning of the Cauchy theory, okay? The Cauchy-Gorsa theory. All right, so let's do it. So what are we going to have over here? So let's parameterize t by the following way. It's really z of t, and this is the easy one. It's just e to the I t. E to the I t traverses the unit circle as t goes between 0 and 2 pi, or negative pi and pi, right? And again, you might say, wait a minute, when you plug in 0 and pi, you have the same value, right? And that makes the curve closed, right? So now this curve is closed. So c is t, and our curve is closed. It's a closed curve, because the starting point and the end point are the same, so it's a closed curve. Okay, and it's easy to see. We already know the unit circle is a closed curve, right? So if this is the real axis, and this is the imaginary axis, then your unit circle is just this. So we're integrating the function as a clockwise orientation, like that. Okay, that's what we're doing. And so now we're in great shape, right? Because now the integral t of z to the power n dz, what do? We integrate from 0 to 2 pi. Z is really what? Z is really e to the it to the power n. And then times dz, that's going to be an I e to the it, because that's what the derivative of e to the it is, dt. And so this is the integral from 0 to 2 pi of I times e to the I t times n plus 1, right, dt. Good. Now, momentarily, so there's two cases to do. This, if n is equal to -1, what's this going to be? If n was equal to -1, which is an integer, this is 0, right? And e to the I 0 is just equal to 1, so this will just give you what? This will just give you an I from 0 to 2 pi, so you just get a 2 pi I. So that's what you get when n's equal to 0, okay? So you get a 2 pi I when n's equal to 0. Sorry, not 0, but n's equal to -1. Now, if n is not equal to -1, then what happens? Then the integral from 0 to 2 pi of I e to the I t times n plus 1 dt is going to be what? Is going to be I, and then e to the I t n plus 1 divided by I times n plus 1 from 0 to 2 pi. The i's cancel out. But this is an integer now. That's an integer. So I have e to the I integer t. E to the I integer t is cosine of an integer t and then sine of an integer t. Those functions are 2 pi periodic, right? So this is 0. Remarkable. Not 0 factorial. 0 factorial is 1. But 0. Okay? So this thing integrates to 0. So in other words, we just showed in the following fact, the integral over t of z to the power n dz is equal to 0 if n is not equal to -1, and it's 2 pi I if n is equal to -1, okay? That's a really important fact, as I alluded to. You can call that a lemma or something like that. It's an easy calculation. There's no serious calculus behind this. Very important. Now, let me sort of generalize. How did I figure that out? How did I know it was going to be 0? So we say, here's proposition. We say that f capital is a primitive of f if f prime is equal to f. And so if f is a primitive, and the curve C is closed, not primite. I spelled primitive wrong. I'm not sure how that happened. That's an A. Primitive. Spelling is not my strong suit. If you've watched me on these videos, I probably made hundreds of spelling mistakes. Primitive. Okay. And C is closed, then what? Then the flow integral of f dz is equal to 0, okay? And the proof of this is just a Calc 3 proof. Proof, integral over C of f dz is the integral from a to b of f prime z of t z prime of t dt. That's a perfect derivative. That's just a derivative of f of z of t, right, by the chain rule. So this is f of z of t from t equals a to t equals b, which is f of z of b minus f of z of a. But that's equal to what? That's equal to 0 because z of a and z of b are equal to 0 because the curve is closed, right? So if a function is a primitive, then the integral over a closed curve is equal to 0. This function, z to the power n, has a primitive. What's the primitive of z to the n? The primitive of z to the n is what? The primitive of z to the n is z to the n plus 1 over n plus 1 if n is not equal to -1. If it's equal to -1, then it's a logarithm. Logarithm gives us a problem. And the reason the log gives us a problem is because it's the inverse function of exponential. You might say, big deal, it's the inverse function of exponential. But complex exponentials are periodic, which means if I go around the circle, there's going to be discontinuity in the argument, which means I cannot define the logarithm everywhere. We're going to focus on the logarithm in further videos, but for the time being, just realize that the logarithm is not, the z to the -1 does not have a primitive in basically in a disk, basically. It's impossible to do that because it would violate the argument principle, okay? But nonetheless, if you have a primitive, right? So for complex line functions that have a primitive, and you integrate a primitive, if you do this integral over a closed curve, you get 0. And that's like the toy version of the Cauchy theorem, right? So we're going to really sort of focus in on this idea, and it really follows from nothing more than basically some ideas from Calc 3, just with a complex twist to them, right? So in other words, all I'm doing over here is I'm just using some Calc 3. Now you might say, well, wait a minute, you haven't specified the regularity. I'm intentionally doing the regularity question alone for a little while until we get to more advanced things, because when you have sort of rough things and want to do analytic, when you want to start doing complex analysis on rough data, then you get into measure theory, and we haven't done measure theory yet. When we do measure theory, we can come back and address the issue when f has rough data and things like that and distributions. It's really beautiful. Beautiful material. It's very important. In fact, most modern mathematics talk about these ideas of like differential equation with very, very rough or distributional data, right? I work on that a little bit. Nonetheless, let's just assume that, for example, f is continuous, then f prime makes sense over here, then these things in that context it works. Suffice is, like, nothing's wrong with z to the n, just a polynomial, right? So for polynomials, all this stuff works out completely fine. Even for bounded functions like sine and cosine, all this stuff works out perfectly well. So we're going to focus on the functions that have these primitives, right? So if a function, f has a primitive, a complex valued function has a primitive, then the integral over a closed curve is equal to 0 if it has a primitive, right? And that's, of course, I need to assume that this primitive exists on some open set, maybe some simply connected set, but I'm intentionally leaving the geometry a little bit vague right now until we get a little bit more analytical tools in our tool chest. So the main feature is that here's how you integrate a complex valued function over a curve. And if that complex valued function can be represented by the derivative of another function, then that function f capital is automatically what? That function f capital, since it exists at every point, that f capital is a holomorphic function. So if we can prove somehow that holomorphic functions, the derivative of holomorphic function is still holomorphic, then I get a lot more leverage out of this. And that's the next sort of focus in the Cauchy theorem, right? So we're going to use this idea over here along with the idea of a power series to exploit to prove the Cauchy theorem and write down the Cauchy integral formula. Thank you very much.